So we have seen the problems on bending stresses in symmetrical section. Now we can see the problems on bending stresses in unsymmetrical sections. You can see the problem number 30. A cast iron bracket subjected to bending as the cross section of I form with unequal flanges. Unequal flanges. The dimension of the section given in the problem. So find the position of the neutral axis and the moment of inertia of the section about the neutral axis I. So if the maximum bending moment on the section is capital M 40 meganewton mm, determine the maximum bending stress, right? And what is the nature of the stresses they asked. Okay. So there will be the bracket connection. The flange is 200 mm and 50 mm, but here bottom flange you can see 130 mm with freedom. So this is unsymmetrical. Okay, so the axis, x-axis is unsymmetrical, but you can see y-axis is symmetrical. So here, if you consider the y-axis, and if you see left side and right side, the dimension will be same. So with respect to y-axis, it is symmetric. But with respect to x-axis, if you take x-axis, so this side bottom and top, if you see, the dimension is different. Therefore, with respect to x-axis, it is unsymmetrical. So here you have to find out the y bar. Okay. So now the given data, bending moment M 40 meganewton mm, the given. Here the section is symmetrical about y-axis, and so y bar is only to be calculated, right? So the y bar, you know how to calculate the y bar, which is nothing but you can divide this I section as 3 sections. This bottom section 1, middle section 2, and top flange section 3. Therefore, y bar is equal to a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. So in engineering mechanics also, you have studied how to find the y bar, right? So here you can see the y bar equal to a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 a3. Now area of the bottom plus suppose the section 1. So section 1 rectangular area is a1. So for this rectangular section 1 a1, breadth into depth 130 into 50. The dimension 50, flange with 50, flange breadth 130. So a1 130 into 50, you will get a1. And y1 is nothing but distance of the center of gravity of the a1 from the bottom piece. So from the bottom, suppose this x-axis, from the bottom, CG of the a1, the a1 cross section, section 1. So CG is 50 by 2, isn't it? At a distance of 25 mm. So from the bottom at a distance of 25 mm, the value y1 will be there. So y1 is equal to 25 mm. And area of the web. So section 2 is web. So A2 is nothing but the web, the depth of the web is from here to here, that is 200 mm. So 200 into, and thickness of the web is 50 mm. Thickness of the web is 50 mm. Therefore, 200 into 50 A2. And Y2 is nothing but distance of the CG of the A2. That is this web area CG. Okay, web area CG means 200 divided by 2. 100 mm distance. Plus this from the bottom. So from the bottom means from here to this flange height is 50. So from the bottom, this is 50 plus this half of the web area, that is 200 by 200. So 50 plus 100. So y2 is 150 mm. So area of the top flange A3. Similarly, A3 means here you can see here section 3 flange cross section 200 by 50. Therefore A3 is 200 by 50. And y3 is nothing but from the bottom CG of this portion. So here this is 50, then this is 200, 50 plus 200, then this is 50 by 2. So 50 plus 200, 250 plus 25, right? 275 mm is the y3. So here y3 you can see 275 mm, 50 plus 200 plus 50 by 275 mm. So now A1, A2, A3, Y1, Y2, Y3, now you can substitute Y bar equal to A1, Y1 plus A2, Y2 plus A3, Y3 divided by A1 plus A2 plus A3. So you will get the Y bar value as 166.51 with respect to bottom. So from the bottom, isn't it? So neutral axis at a distance of Y bar is 166.51 mm from the bottom face. That is from the bottom Y compression YC is equal to 166.51 mm. So now the distance of CG from the upper top flange, okay, that is overall depth minus this Y bar, isn't it? So total overall depth is 300 mm minus this 166.51, so 133.49, that is YT. Okay, so now the moment of inertia of the section about the neutral axis I. So I is equal to, you have to calculate I is equal to nothing but I1 plus I2 plus I3. So now we can calculate I1. So I1, how to calculate moment of inertia of the bottom flange about the neutral axis. Moment of inertia of the bottom flange about the neutral axis. So here I1 is nothing but BDQ by 12 plus A1 into Y bar minus Y1 the whole square. So here BDQ, so bottom flange, the bottom flange width is 130, bottom flange depth is 50. So 130 into 50 the whole cube divided by 12 plus A1, 130 into 50, 6500 into Y bar. So from the bottom to the neutral axis depth is Y bar, that is 166.51. Okay, so minus Y1. So what is the Y1? Already you found Y1 is nothing but 25. So here you can see in this diagram, you can understand the distance. So from the neutral axis here to here, this is the distance. Suppose this is the section 1, moment of inertia I1 we are calculating. So in this section, half of the portion to the neutral axis. So half of the distance of this section to the neutral axis. Okay, that distance we are calculating now. So the total distance from the bottom to here is Y bar, that is 166.51 minus this distance. We have to deduct this distance, that is 25, 55 to 25, the whole square. So that is how we have to calculate. So now you can see here Y bar minus Y1 the whole square. Okay, that is moment of inertia 1. I1. I2 means moment of inertia web about the neutral axis. So similarly, BDQ by 12 plus A2 into, similarly, this Y bar minus Y2 the whole square. So here you can see the distance is BDQ by 12, web, breadth of the web is 50 into depth of the 200 the whole cube 12 plus 50 into 200 area of the web 10,000 into the distance. Okay, you can see second 166.51. So here this distance is 166.51. So here the distance between the center of the section 2, we are calculating the moment of inertia I2, therefore web. So in this web, half of the distance, in this web, half of the distance, okay, from that half of the distance, suppose this one, in this web, the half of the distance is this one, okay. So here, this total Y bar is 166.51. So here, this distance is how much? From here to half, okay. So total 300, right? 200, 50, 50. So half of the web is nothing but white 150, 150 mm. So from the bottom, the half of the web section 2 is 150. So we need the distance between this half of the distance to the neutral axis distance. Okay. So total 166.51 minus this 150. So if you deduct, you will get this distance, right? So that one is whole square. So I2 here. So 166.51 minus 150 the whole square. Similarly, I3 moment of inertia of the top flange about the neutral axis. Similarly, BD cube by 12 top flange breadth 200, top flange with thickness 50. BD cube by 12 plus A3 250 into the distance between the center of the section 3, okay, to the neutral axis distance, okay. So from the bottom to the center of the third section, center of the top flange is 275. You can see here. And see here, from the bottom here, this distance is how much? 275. But the distance is the 275. We need the distances from here to here. So from here to the neutral axis is, from here to the neutral axis distance is 166.51. But we need the distance between the center of the third section to the neutral axis. So center of the third section to the bottom is 275 minus this neutral axis distance 166.51. You will get that distance. So I3 will be the 275 minus 166.51 the whole square. So you will get the I3 value. Therefore, I is equal to I1 plus I2 plus I3. So you will get I value, moment of inertia value. So after finding out the moment of inertia value, so here you can see this is the distance 133 YT, this YC, and this YC will be 166.51 mm from the maximum bending stress for the maximum distance. So using bending is m by I equal to sigma by y. Sigma is equal to m by I into y. So in the problem they are asking to find out the bending stress sigma b. Sigma b is nothing but m by I into y. So m value given in the problem, I value you calculated, y value y bar 166.51 So y bar compressive. So the stress will be, the nature of the stress will be compressive, YC. From the bottom, YC is 166.51. Because Y is the Y maximum. Here Y maximum is 166. So that will be under compression. So in case of cantilever, the upper layer is subjected to tensile stress, whereas the lower layer is subjected to compressive stress. Since we can assume that this one is cantilever. So if you assume this as a cantilever, then the compressive will be at the bottom. Okay. Sigma B value is 23.377 Newton per mm. So this is how we have to calculate the bending stress value. So only thing is the how to calculate the y bar value. That is okay. That is important. Problem here. So y bar a1 y1 plus a2 y2 plus a3 y3 b1 plus a2 y3. Then the moment of inertia. How to calculate the moment of inertia value. I1 is BD cube by 12 plus a1 into y bar minus y1 the whole square. This formula you should know. Then you can easily find out by using the relationship m by I equals sigma by y. You can be able to find out the sigma value, right? So I hope you understand.